an 8-bit computer in Logisim-Evolution. So, in the last episode, we made the ALU using a half adder, full adder, 4-bit adder, and then eventually changing that to make an 8-bit adder, and then making that into the ALU so it can subtract 2. So, in this episode, episode 2, we're going to be making the RAM, which stands for Random Access Memory. And since this is a Harvard architecture computer, we're going to have 2 different types of RAMs, the instruction RAM and the data RAM. So the instruction RAM and the data RAM are like technically the same thing. They're both RAM that are like exactly the same hardware, but they perform different tasks. The instruction RAM is like the instructions which tell the computer whether to like add, subtract, or like store, load, and then the data RAM is just the data, like what number do you want to add or what number do you want to load. So the RAMs are exactly the same for those. We're just gonna be using the same RAM. We're only making one RAM today and using that for both. So the first thing we're gonna be making is the SR latch. And the SR latch is gonna be made with 2 NOR gates and 2 input pins, reset and set. So this is gonna be reset and this is gonna be set. So reset goes in the top input of the first NOR gate, and then set goes in the bottom input of the second NOR gate. And then 2 outputs, Q, which is your data output, and then not Q, which is just the inverse of whatever Q is. You can't put a minus symbol in to name pins, so I just put N instead, and then Q. And then now we have to take the wire from here and like flip that into here so it can kind of like store memory. And if the wires ever become red like that and it says oscillation apparent, you can just turn on one of the pins, go to simulate tab over here, and just spam this button and it should work. But make sure the simulation is unpaused. So now if we test it, if we reset, then Q is 0, and if we set the data to 1, then Q is 1. So that's all working. So I'm going to save this, Command S, and then we can make our next circuit, which is the D latch. So the D latch is going to be using one SR latch, and it's going to have 2 inputs again, and these ones are called data, which is just D, and enable. So what's gonna happen is that we're gonna have to have 2 AND gates. Like this. One of them going to reset, and one of them going to set. And then what I'm gonna do is use a NOT gate on this top one, like this. And for this one, it's just going to be the normal D. And these 2 are going to be connected. I'll fix that in a sec. These 2 are going to be connected like that. So now you can just turn on one of the buttons, enable, and just spam that button. So now, okay, wait, let me attach the outputs first. So they're going to be the same outputs, Q and the inverse of Q. So when Q is 0, the inverse of Q should be 1, so that's right. So now if enable is off, this should not work, because enable's off, but enable's on, and we put in our data, it should, wait, that's kind of weird. Oh yeah, enable has to be off for that to work, guess. Okay, anyways. So yeah, that's working. So if Q is 1 and you want to make it 0, then you can just, like this, we're going to eventually make this the clock button. So the data, Q will be 0, and then if you want it to be 1, then Q will be 1. So it's working. I'm going to save this. And then the next thing we're going to be making is our D flip-flop, which is going to be using 2 D latches, like this. And we're going to have 2 inputs again. This one's going to be data, and this one's going to be clock. So let me see here. So the data goes into the data of first D latch, and then the Q output goes into the data of here as well, like that. But for this, we're gonna not this input, so it can be a rising edge clock, and then the actual value comes to the enable of here, and then we can forget about the not Q because you don't really need that. I'm gonna label them the same. Okay, there we go. So now if I go like this, yeah, see now it's clock triggered. Like before, if I had it, the data at 0, and if I want the data to be 1, right now Q is 0. If I want the data to be 1, I clock it, right? That works. But if I turn off the data in the D latch, it would go to 0, but now it's not because the clock hasn't been pulsed. So when the clock's pulsed, then only can the Q become 0. So that's all working. This is our D flip-flop, and I'm going to save this, and then we're going to make one more component, and then we're going to make our 1-bit register. So this one's not really a memory component, it's a multiplexer. So I'm going to name it 221 multiplexer, like this. So for this, we're going to have 3 inputs. So we're going to have S, which is our like control wire, and then we're going to have this is going to be new, wait no, this is going to be old Q, this is going to be new D data. So what we need to do is that whenever S is off, whenever the control pin is off, we want old Q to be passed through. So what we're gonna do is not this, just like this, and then pass old Q through here. And then second AND gate, so when S is on, we want to pass new D in, or new data. And then we need an OR gate at the end. So if either one of them is on, it's on. And then that output is just output. I'm not gonna label that. So let's test it. So if S is 0, new data shouldn't change anything. It should, since S is off, but this should be 1. But if the control is on, then this shouldn't do anything, but this should. So yeah, it's working. So I'm gonna save this. And then the next thing is the 1-bit register. So for the 1-bit register, we're going to need a singular D latch or multiplexer and a singular output, because we're going to forget about inverse of Q now because we literally do not need it. Actually, before I do this, there's one more thing we have to make. I'm just going to delete the 1-bit register. It's going to be a clear D flip-flop. It's really simple. It's a really simple circuit. It's just a D flip-flop that's able to clear. So for this one, we're going to have 3 inputs. It's going to be data, your clear button, and your clock. So clock just goes to clock as normal. But for the clear and the data, we're going to use an AND gate and not the clear. Wait. Yeah, not the clear. So the clear is always on, and then the data goes through here, and then this goes through here, and then you have to use your output pins. Q and not Q. So how this works is that if you want your data, obviously, this should just, it should work as a normal D flip-flop. But if you ever want to clear it, like turn everything off, you just have to press clear and then clock, and it should clear whatever is there, because the AND gate, if clear is on, the AND gate will always output 0, which will make the data 0. So then whenever you clock it, the output Q will always be 0. So this is the D flip-flop we're going to be using. So I'm going to be saving this, and then I'm going to make our 1-bit register circuit. And I'm going to use a clear D flip-flop and a multiplexer. So we're going to have a few inputs. So this is going to be our data. This is going to be, actually no, we need a fourth one. This is going to be enable. Right. I'm actually going to switch these two around. That makes more sense. Clear. We're going to make this clock first. And then clear. Like this. And then your data. So all that's happening here is the clear just goes to the clear. Clock just goes to clock. Always. What write and enable do is that you want to use an AND gate to AND both of these. So basically what that's saying is that only if both of these are on can it actually do anything with this register, and that's going to go into the control of our multiplexer, and then the output of our multiplexer will go into our data. So our new data will be this one. So when this is on, it can store the new data, and then we can bring our output like this, and this will go into old Q. Okay, there we go. That's basically it. So now what's gonna happen is that only if the data will only store if write, enable, and clock, and the clock is pulsed. Only if all of those are on. So if let me just clear this for a second. Okay, wait, I probably need to. There we go. Yeah, the clear is good. So if you want to store, let's say 1, right? But if you just click the write, it won't do anything. Just the enable won't do anything, and just clocking obviously won't do anything. Clear will just not do anything either. But only if all of them are, only if write and enable are on and the clock is pulsed, then only can it store data. And same for when you want it to be 0. So, and then if you want to clear it, you can turn this off, clear, and then like that. So yeah, that's our 1-bit register. So I'm going to save this. Next, I'm going to make the 4-bit register. So I'm going to use 4 1-bit registers, and from now on it's just a bunch of wiring. You don't really have to do anything. So that's going to be there. Those are going to be your 4 data inputs. Trying to do this quick, so there's not too much wiring. So the data goes into here, and then we're gonna have write, enable, clock, and clear. So I'm gonna actually label all these. clock, and clear. So then these all go into here, but they also have to go into these ones too. So right just goes, okay, that's probably a bad place to start. Right goes into here, enable, clock. Okay, that's actually a bit messy in what I'm doing. And then clear, I'm just gonna start all the way here. And then the right of this has to be connected to the right here. Enable has to be connected to enable. And then clock is this one. And then same for this one. So right is this one. Enable is this one, and clock is this one. So now all we have to do is not take an input pin, take 4 output pins, and those will be our output. And then we're going to be chaining 2 of these 4-bit registers to make an 8-bit register, and then using 4 8-bit registers to make our RAM. Getting close now. So then these come here. And now let me just clear all this. Let's say you want to store this value. You have to write enable end clock, and it should store that value. And then if you want to clear, just clear and then clock. So that's working. I'm gonna save this, and then I'm gonna get straight to our 8-bit register. And then we're just gonna need 2 4-bit registers, basically the same wiring. Except now we need 8 inputs. I'm just gonna copy and paste those. Here we go. So first 4 go into the first 4 of your data. Three, 4, and then the second 4 go into the second 4 of your data, of your register. And then we're gonna have our write, enable, clock, and clear again, obviously. Okay, that's... I'm gonna label these write, enable, clock, clear, and then write goes to write, enable, clock, clear. And then now I'm just gonna get 4 more of these pins, and then copy and paste them, and these will be our output. Okay, there we go. So you can clear all of this and then put in some random value. Okay, there we go. That's the same value. Yep. Nice. So I'm gonna save this. And next is our, so we're gonna have to make a 2 to 4 decoder because we have to select our address in our RAM. So we're gonna make a 2 to 4 decoder. So obviously it's gonna have 2 inputs and 4 outputs. So we're gonna need 4 AND gates. And then 4 outputs. trying to go quick because this video is already really long. 3, 4, and then these will be your 2 inputs. So when both of them are off, you want the first one to be on. So we're gonna have to move this NOT gate way up here. We want the first AND gate to be on so that this one can be on. And then when it's 0, 1, when this one's on, this will have to be here, and then use a NOT gate for this one. So that's 1, and then 2. So when this one's on, but this one's off, we're gonna have to NOT this one, the bottom one, and then when both of them are on, it should just be going into here. So that should be it. So when it's 0, 0, 1, and then when 0, 0, this one should be on, 0, 1, this one should be on, 1, 0, this one should be on, and 1, 1, this one should be on. That's literally it. That's our decoder. So yeah, I'm gonna save that, and then now we can finally get to our RAM. Oh yeah, you can't use RAM. We can just use RAM. RAM S, sure, because it's technically 2 RAMs. Okay, anyways, we're gonna have 4 registers in our RAM. That's an okay amount. It's not too much. It's enough to run basic programs. And we're gonna have to have our address selectors with our decoder. So this goes into the enable of the first one. This goes into the enable of the second one. This one goes into the enable of here. And then this one goes into the enable of here. That's our addresses. Then our data. So this might take a while because you have to wire up all these data wires, but I'm gonna make this maybe slightly faster by using a splitter. So if you go to wiring and you take a splitter, you can make it facing west and make both of the fan out and bit width in 8. So now you can make a data bus. So just connect all of these up to here. Like that. And that'll be your data bus. So I think I'm just gonna bring it behind all of this to here. And then now we can split it, resplit it back. So this actually might take a long while. So just connect this. And then just repeat that for the rest of them. So bring this wire down, get another splitter, face it west, 8 and 8. All we're doing is creating a data bus and then unsplitting the data bus, I guess you could say. Well, no, you're splitting it back into 8 wires. Also, make sure the dots on the end of these are not gray. It's kind of hard to see. But if they're gray, that means they're not connected. That's the second one. Get the third one. And then the last one right here. You could always add more addresses if you want, but it'll take a long time. Like 16 well, the max number of addresses you can have in an 8-bit computer, or the max number of like RAM registers, is 255. If you surpass that, yeah, making 255 is gonna take a long time anyways, which I don't really have right now. So that's all. That's all of our data lines connected, and then we can just make the same thing as last time. Write, clock, and clear. We don't have enable this time because enable is handled by our address selector. So I'm gonna name this write. Wait, I don't like it lowercase. Write. Why is it doing that? Okay, I don't even know. Right. Clock. Here. Oh no. Okay. So clear. Guess we can start with clear. This should go to the clears of every single one. It's like a universal line. Just quickly do that, and then clock should also universally go. So should write. All of them should actually. Clock. And then write. But the thing is, since we have multiple registers and only one output bus, we're gonna have to use something called tri-state buffers, which make it so that only one register can be like outputting onto the output bus at once. So that kind of makes sense. I don't know. So I'm gonna take 8 output pins. I'm just gonna take 4 and then copy and paste these. And that's gonna be our output pins, and we're gonna have to use tri-state buffer. So if you go into the gate section on the side, it's something called controlled buffer. You need 8 of those for each one. So I'm just gonna make 4 and copy and paste it. Not do that. Okay. And then I'm gonna copy and paste this 4 times so we don't have to keep making them. There we go. Okay, so now all we have to do is just connect these wires to here. And then connect these outputs to our data outputs. Like this. Just some basic wiring. Like this. And then the control line of all of these, which is this little thing right here, should be the control line for all of them. And then that should be connected to the enable. So when that register is enabled, only then should it show its values. And then same for all of this. These ones. Except for these ones, you can just connect it up to here because they're all already connected to the outputs. Just make sure you don't miss a line. That's good, and then you can do the same thing except with this register's enable line. Oh. And then use this one's enable line to connect to here. And then the same for this one, and then same for the last one, and then our RAM is done. It's actually faster if you just take the lines like that from there as well. Okay, I don't know why this one doesn't want to. Okay, and then same for this one's control line. Just connect those all up. And then the enable line. And then last one. And then we can test out our RAM. This has been a really long video, so sorry if it was too long. Try to go as quick as possible. Okay, this might be a bit of a tight. It's fine. Okay. And then last, we just have to connect all of these up one last time. Don't do that because that's really bad. And then connect the control to your enable line. This part of the computer is probably the most time-consuming part, if I'm even gonna be honest with you. There we go. So that's everything done basically. I'm gonna zoom out a bit. So for our test, let me first clear everything to check clear and clock is working. So everything should be cleared now. And let's say an address 1, right? We want to store everything as 1. There we go, yeah. So we stored everything as 1, but in address 0, we want to store just the top one as 1. So right and clock. So there we go. But now we want to see, I forgot what's in address 1. Obviously it's just full, everything's 1. We want to see what's in address 1 again. So there you go, that's what's in address 1 and that's what's in address 0. And then if you clear everything, there should be nothing in address 0, nothing in address 1. Okay, so that's it for this episode. Thank you for watching. Bye.